Okay, so sorry about that. There we go. So yeah, my name is Bob. I'm going to stand here. And let me start with a question, actually, because I'm curious. So who of you has used Wikipedia in the last, say, week? Whew. Okay, good. It's a dangerous question to ask at the beginning of the talk, because this is going to be all about Wikipedia, and if there had been crickets, then that would have been embarrassing. Okay, so your hands show that Wikipedia is an important resource. And in particular, as you probably know, Wikipedia is the largest encyclopedia in human history, and it's actually the 5th most visited website in the world also. There's a version of Wikipedia in close to 200 languages. About 160 of them are actively edited by people, totaling over 40 million articles. And the English edition alone contains over 5 million articles these days. And due to these impressive numbers, people tend to think that Wikipedia is more or less complete, especially English speakers think so, because the Wikipedia in English is just so large. But this is actually not the case. So let me show you what you can really learn about the world in Wikipedia for different languages. So this is a map of the world where any Wikipedia article that has a GPS coordinate associated with it is shown as basically a small yellow dot. For example, there's a small dot for Lausanne, which I put here. It's red just to emphasize it, but that's because there is a Wikipedia article about Lausanne in many languages. So this map represents all the places in the world you can learn about if you could read any Wikipedia article in any language. So for example, all of Switzerland is brightly illuminated because there are a lot of articles about Switzerland in many languages. But as you can see, there are many densely populated areas in the world, such as India, China, Southeast Asia, South America, that are not well covered by Wikipedia. And the problem gets even worse if you speak only one language. This is combining all the languages. For example, if you understand only German, then these are the places in the world that you can learn about by reading Wikipedia. So you see that that's mostly focused on Central Europe. If you speak only Spanish, then this is what you can learn about by reading Wikipedia. Surprisingly little light action in South America, which was surprising for me. And if you are an Arabic speaker, then this is what you see about the world. So there are nearly 500 million Arabic speakers on the planet, but their access to knowledge through Wikipedia is severely limited, as you can see in this dark map. All right, so although I focused on the previous slides on content that can be geolocated, that has GPS coordinates associated with it, we have the same massive gaps in content in other domains too, such as the sciences, arts and humanities, and so on. And the bottom line is that depending on the language that you speak, you can only learn about a small subset of topics. And the question is, how do we address this problem? How can we make access to all knowledge universal across all languages? In other words, the challenge is to amplify the growth of Wikipedia, especially the growth of smaller language editions. And in this talk, I will present a system that can do exactly that. All right, so here's an overview of our system. In particular, our system encourages Wikipedia editors to create important articles that are missing in their field of expertise and in the languages that they speak and can write. And the system consists of 3 components. The first component finds articles that are missing, because those are the ones we want to create. Then in the second step, we rank those missing articles by importance, and in the third step, we recommend the most important missing articles to those editors that are best suited for creating those missing articles. And we then empirically validate the system in a large-scale controlled in vivo experiment that was run actually on live Wikipedia. And we show that we can increase the creation rate of new articles by a factor of 3, with no loss in the quality of the articles. Okay, so in what follows, I'll walk you through each of these 3 components, and at the end, I will discuss the results of the in vivo experiment. Okay, so the first component of our system involves finding missing articles, or more precisely, finding articles that exist in certain languages, but that do not exist yet in other languages, such that we can then transfer content from those existing versions to the non-existing one. Okay, so to do this, we use the Wiki Data knowledge base, which you may think of intuitively as a database version of Wikipedia. So that's instead of having like this unstructured text, it's a structured database. And to create Wiki Data, volunteers have, among many other things, mapped every Wikipedia article in every language to nodes in a language-independent concept graph. So in this toy example up there, you see that the Apple article in Dutch, English, and Slovenian Wikipedia they all map to the same language-independent concept in Wikidata, which is identified by this abstract code Q32. Right, so in this hypothetical example, you can see that the Apple concept is mapped to an article in English, but not to an article in French Wikipedia. So English is in this left box, French on the right. Okay, so that means that the Apple article is missing in French and it's a candidate for creation. And by the way, throughout this talk, I'll use French as the target Wikipedia that we want to enrich with new articles that we want to grow. All right, so that was pretty straightforward. But this find step that I just described can easily generate millions of missing articles that are missing in all the languages. But at the same time, there are only a few thousand Wikipedia editors that would have to do all the work of creating those articles. So clearly that won't work. There are too few people for too much work. So we need to prioritize, and that's exactly the goal of the second component. We want to rank all missing articles such that we can focus our efforts on the most important ones first. Okay, so this then identifies the high impact articles that basically would have the largest delta in terms of knowledge added to the world, illuminating this dark map in the beginning. Okay, so the task that we need to solve is the following. Given a missing article in the target Wikipedia, the Wikipedia that we want to grow, predict where in the popularity ranking the article would fall if it existed. Well, it doesn't exist yet, but we're predicting how much would it be viewed if it existed. And to be clear, we generate a separate ranking model for each target Wikipedia. This is because different language communities have very different notions of importance. For example, country music is very popular in the English Wikipedia because a lot of those viewers come from the United States, but the French Wikipedia probably doesn't care that much about country music, so you should probably put more effort on wine and cheese and things like that. All right, I'm again priming you for lunch, you know. Okay, so this way we make sure that articles that are created are important to the actual readers of the respective Wikipedia. Okay, so this sounds great, but the catch and kind of the whole point is that the articles that we're trying to rank don't even exist yet. So that also means that we can't extract features from those non-existing articles that we could then use in a machine-learned ranking model. So we need to be just a tad smarter. And what we do is the following. We build a machine learning ranking model that predicts the observed rank of articles that already exist in the target language, but using features of articles for that article in other languages. So that means that once we have the model, we can also run it on articles that don't exist yet in the target language, because all the features are derived from all the other languages in which the article already exists. Okay, and the features that we use concretely include things like the numbers of page views of the article in the languages in which it already exists, then content topics that we extract via certain kinds of topic models, LDA is what we use here, and we also use features that are extracted from the link network formed by the articles that link to each other. Okay, and then once we have these features, we stick them into a standard random forest classifier, and after training the model, we can then apply it to an article that is truly missing, and we get its predicted popularity rank. And then we can rank all the missing articles by predicting popularity and ask editors to create the most important missing articles first. All right, so in the third step, we actually do this recommendation. So we have the missing articles and we have importance numbers for all of them, but we still haven't created any of them, right? And so that's the next step. So we really want to encourage editors of Wikipedia to create those articles first that are ranked highly. And we do this by recommending to people those articles that are most aligned with with their preferences, with the topics that they have liked to edit historically. Wikipedia has all public logs in terms of like the edit history, so we can look there who edited what articles, and we want to recommend those articles to you that are similar to those articles that you've already worked on previously. Okay, so specifically, to make recommendations, we solve a bipartite matching problem between editors on the one side, on the left side of this depiction here, and missing articles on the other side. So we have this bipartite graph of editors and articles, and it's fully connected. So each editor is connected to each article, and each edge is weighted by a number that captures how interested we think that editor is in that article. And for now, just assume that these affinity numbers they fall from the sky, some oracle gives them to us. On the next slides, I will tell you how we actually compute those. Okay, and then in the formulation of this matching problem, we ensure that each article is assigned to at most one editor to avoid editing conflicts. We don't want several editors, we don't want to direct several editors' attention to the same article, because that would, then they might clash. And we also ensure that, that each editor receives a certain small number, a fixed number k of recommendations. Right, and then given these constraints, we maximize the sum of affinities. That is, the quality of the total matching between articles and editors. And we can write that down as a linear program, which you see here on the right, but please ignore it. I just added this to follow advice from a teacher of mine, Luc Devroy, who once said that every talk should contain an equation and a joke, and they should not be the same. So here you go. It's my tribute to Luc. Right, so now you may wonder, where in this formulation do we make sure that important articles are actually prioritized? Because right now it's not in there. Well, that's where this word top at the top of the slide comes in. The simplest way of incorporating article importance into this framework is to simply just include on the right-hand side the most important articles, that given those numbers that we've computed in the previous step. And that means that using fewer articles ensures that we assign the most important articles first, and using more articles there makes it more likely that every editor gets a recommendation that really is in tune with what they want to do with their interests. There are more sophisticated ways of doing this too, but that's the simplest one, and it actually works quite well. All right, so up to now you've made a leap of faith and assumed that those affinity values that weight the edges in this bipartite graph exist. They come from somewhere, and now on the next slide I'm going to tell you how we actually compute those. So to do this, we first generate a vector space embedding of all concepts. So concepts you can think of as like language-independent versions of Wikipedia articles. And we construct this embedding such that semantically related concepts have similar vector representations, such that they're close to each other in this vector space. All right, so and in our case, we use topic modeling, LDA, to get these vector embeddings. But you could also use more recent neural network-based techniques such as word2vec and so on. Right, and what you see here in gray are the 2D projections of the vector representations of 4 concepts. And now let's say that an editor, E1, has recently edited articles corresponding to the 3 concepts depicted in blue. And by averaging these embeddings, we can basically get an embedding of the editor. So that's the position of this little person icon there. All right, and now the affinity that an editor has for a concept, so the E1 and the concept Q34 can simply be computed as the cosine similarity of the 2 respective embeddings. And right, so this closes the small parentheses on how we compute the editor to article affinities. And we're going back to the big picture. So next, I will show you how well this actually works in practice, but before that, let me briefly summarize what we've seen. So we have a system now that works in 3 steps. It first identifies which articles are missing in what languages in Wikipedia. Then, for a given target language that we want to enrich, we rank all the missing articles by their predicted popularity. And then finally, we match the missing articles to those editors that are most likely to be willing to contribute to creating those articles. All right. So next, we would like to see how well does this system actually work in practice. So I should say that this work was done in collaboration with the Wikimedia Foundation. So that's kind of the mothership of Wikipedia, and they have a real interest in making these things work in practice. So it's not just a research project, it's also there to really improve Wikipedia. So we want to test this in a robust way to justify to them that they should actually run this system in reality. Right, so what we're going to ask is, what impact does deploying such a recommendation system have on increasing the rate at which missing content is created and knowledge gaps are filled in Wikipedia? And to answer this question, we ran a large-scale experiment in French Wikipedia. So we want to make French Wikipedia more complete in this case. And we contacted 12,000 French-speaking Wikipedia editors by email, and we sent 5 recommendations to each of them, so recommendations of articles to create. And the easiest way to create a missing article is to just translate it from another language. So we explicitly suggested to those study participants, or like involuntary study participants, to use a content translation tool that's made by the Wikimedia Foundation. All right, and as I said, we only contacted editors where we have evidence that they speak French. All right, so the research questions that we want to answer is: first, do recommendations boost article creation rate for REAP compared to a scenario where there are no recommendations and Wikipedia is growing naturally, organically? Second, how much does personalizing recommendations increase editor engagement? And third, how do recommendations affect the quality of the articles that are being created? Right, so here's a depiction of our experimental design. So there are 12,000 French Wikipedia editors that we emailed, and we took the 300,000 most important missing articles in French Wikipedia, and we randomly put each of those, the editors and the articles, into 3 experimental groups. And there is, so this gives rise to 3 experimental conditions. The first one, in green at the top, is the personalized recommendations condition. That's basically deploying our system. So here, articles were recommended to editors using the affinity-based matching method that I just presented to you. In the second condition, called the randomized recommendations condition, articles were also recommended via the matching method, but not with personalized affinity scores, but with randomized affinity scores. And in the third condition, there are no recommendations at all. So we just let Wikipedia run organically, basically, in that third condition. So no articles were recommended, and no editors received any recommendations. All right, so comparing the first to the third condition, so personalized recommendations to no recommendations, lets us basically evaluate the impact of our system. This is like how much more knowledge gets created with our system compared to not using it. Comparing the first and the second condition, so personalized versus random recommendations, lets us evaluate the impact of recommending the right thing versus just recommending something. You know, it could be that people do the work just because they ask them to do something. Maybe it's not our recommendations that make the difference, but that we can check this way. Okay, and then if we compare conditions 2 and 3, we can see the difference between recommending something and recommending nothing at all. All right, so since we sent 12,000 unsolicited emails in this experiment, obviously we got quite some feedback. So this guy here actually really liked what we do. You know, I can't even read this. You know, very nicely done and so on. Some people didn't like it. I'm not going to read this out. I'm going to leave this to the French speakers of you to ingest, so pardon my French, kind of. And some people specifically complained because the recommendations that we gave them weren't good. So this guy says results are catastrophic. But then we checked, and thankfully this guy was in the random control condition, so everything was still good. Okay, so here are the numbers. The first research question is, does recommending articles for creation increase the rate at which they are created compared to just the organic growth rate of Wikipedia? And here we define creation rate as the fraction of articles that were missing before the experiment and that are created within 1 month after sending out our recommendation emails. And you see that we achieve a rate of 1%. So 1% of the articles that we recommend actually get created. Now you might think that this is actually a low number, but you got to consider that creating a Wikipedia article takes significant commitment. And so 1 in 100 recommendations that we send out actually got picked up. And in particular, this is 3 times as high as the probability that a given article is created organically. So that's only 0.3%. So that means that we can boost the creation rate of Wikipedia articles by a factor of 3. And so put differently, currently the size of Wikipedia is projected to double within 12 years. So this is typically the time span of this exponential curve. But if we can sustain the boost with our system, then this will happen within 4 years, so by the end of 2021. Okay, so in the interest of lunch, I'm gonna skip over this slide. You know, it works, blah, blah, 2-fold boost in activity, and so on. That's nice. And there's no decrease in terms of the article quality, because you might think that if we tell people to do something, that they might do poorer work, because it's not coming intrinsically from them. But that's not the case. The quality of the articles, and we checked automatically and manually, is the same as if the article gets created by someone intrinsically. And then finally, we actually turned this into a tool. And let me see, this is bad with this. Okay, let me do it this way now. I'm gonna mirror my display. Okay, great. Because we actually built this thing, and so I want to show it off. So should have preloaded the URL. Recommend WMF Labs. There you go, thanks Google. Okay, so here in this tool called Gap Finder, you specify a language that you want to translate content from. So this should be a language that you understand. And here, the target language is the one you want to translate content to, okay? So let's say we want to translate to French because we're in Romandie. So we pick this here. And now it gives, if we type nothing more, it just gives us a ranking of, or a set of articles that should be created. Those are basically the outputs of our system. So Darth Vader, this is a crucial gap in knowledge, obviously. But since we're at the machine learning days, I'll search for machine learning. Okay, why doesn't this autocomplete? Preparing article recommendations. Is this computer online? Yes, it is. Okay, great. So now it gives us, I seeded the system with machine learning. So that indicates that I want to create articles in French that are similar to the article about machine learning. And these are basically all articles that are missing in French Wikipedia, but that exist in English Wikipedia. So for example, what do we have here? Training set, neural computation, learning automata. Actually, let's see what happens if we do deep learning, because this is the hot topic. And then you see, long short-term memory network. So Jürgen Schmidhuber is going to talk right after me. So if you want to make him happy, then you can translate the English version of LSTM networks to the French version. Or something different. Let's say we speak Malagasy, which is the language that's spoken on Madagascar. And we know that Madagascar is going to be hit by global warming. We still believe so, although some important people don't think so anymore. So we see that in the Madagascar version of Wikipedia, there's no article about climate change. There's no article about greenhouse effect and so on. And so this highlights that especially in the smaller versions of Wikipedia, we can actually make a big dent by finding and filling the important knowledge gaps. Those are the people that are going to be hit mostly by climate change, and they don't have a lot of the important information about it. So there's actually a lot that can be done. Okay, so I'm 5 minutes over. I'm going to stop here. I'm not going to switch back to my thank you slides. I'm just saying thank you. If there are any questions, I'm happy to take them, and otherwise, bon appétit.
So my question is that the choice of your learning technique that was random forest, basically, it was you just tried different models and you chose it, or
we tried support vector machines, we tried logistic regression.
Basically, you compare and then you come up with this.
Exactly, but random forests on many applications just seem to be the most robust, so we chose that.
Okay.
Yeah.
Somewhere there, and more, but I think in the interest of lunch. Thanks a lot. I just cannot help noticing that it's kind of putting machine learning problem upside down. Normally, you want AI to solve hard problems for you, but here, like AI uses people to solve hard problems.
Yeah.
But the question is, the second part of your project, when you evaluate the importance of the article, did you do any evaluation of how well you solved this problem?
Yeah. So I skipped that over because I wanted to focus a bit more on the practical application in this tool. But yes, we evaluated that, and so basically you get a rank correlation. We're predicting the popularity of an article for after it gets created, and we can do that. So basically our ranking that's predicted has a rank correlation of 90% with the true ranking. And just for comparison, if you take a very simple baseline model where you basically just use the ranking in English to predict the French ranking, so you do nothing specific to French, then you would get a correlation of only 67%. So doing the machine learning actually helps a lot. And I'd just like to add a small comment on the first thing that you said, that it's machine learning upside down. It's right, but it's more of I think of this more as an ecosystem of algorithms and humans. Because if we want to push something into real Wikipedia, this just won't happen if we don't embrace the fact that stuff needs to be vetted by humans. So if we're just going to write a research paper, then yes, we could totally have done something that would have, maybe even used machine translation and so on to generate those articles autonomously, but that's not going to work because the assumption is that everything that goes into Wikipedia needs to be at least checked by a human. So that's why we said, okay, let's embrace that fact and let's make sure that the limited workforce that we have does the optimal work. And I think that's a very promising paradigm for these types of systems that are run computationally, but also have humans as a fundamental component within them.
All right, thanks very much.
Thank you.